Hi, welcome to the fourth and final video from section 5.1. This video is going to focus on how we can simulate observations from a particular distribution. In order to do so, we rely on the result that is in section theorem 5.1-1. This theorem tells us that if we have a random variable y that has a continuous uniform distribution on the interval from 0 to 1, and we have a function, capital F of x, that has the properties of a continuous cumulative distribution function. And so that would be that, it's for the sort of lower end of some support, the f of a, the lower end, would be equal to 0. For the upper end of the support b, f of b would be equal to 1. That the function would be strictly increasing over the support between a and b. And just to note that it is possible that we could have a situation where our support went from negative infinity to positive infinity, or that one or both of those could be sort of infinite in their direction. If we then take a random variable x equal to the inverse f of y, then this random variable x will have a continuous random variable, and it will have the cumulative distribution function given by f of x. So we are going to be able to use this to simulate distribution observations from a particular distribution. And I just want to talk a little bit about the idea behind doing that first. So here we have x and f of x, right? And this is our cumulative distribution function, f of x, capital F of x, right? And we've got this monotone increasing function between 0 and 1 on this interval. And the idea is going to be that if I randomly choose a number in the interval between 0 and 1, because I randomly choose a number, that if I go across to f of x and I take the f inverse at that value, so here's our y. If I take f inverse of y, down here it's going to give me an observation on this distribution. We can kind of see that if I'm someplace where the curve is very steep, there are going to be a lot of values in this uniform distribution that are going to map to that area of our x. If I have a place where the distribution function is not very steep, right? That would mean that the probability is kind of small in these areas, and so I wouldn't have the cumulative probability adding up quickly. And there are going to be sort of not very many values along this uniform distribution here that are going to map to it. So the idea is that we're going to, in order to simulate observations from a distribution that has a probability density function, little f of x, what we're going to do we're going to start by finding the cumulative distribution function of x. We do that, remember, by integrating the little f of x over the support. Just as we did back in beginning of chapter 3. Once we've got the cumulative distribution function, we're going to generate observations from a uniform distribution on the interval from 0 to 1. There are a number of ways you could do that. If you are someone who is a programmer, you could program something that will generate a number between 0 and 1 and make all the numbers between 0 and 1 equally likely. So that's something you could program. It's something you can also find in online random number generators. I'm going to show you output from random.org's webpage that they actually have a random number generator that will do this for you on there. Once you've got your observations from a uniform distribution, then you're going to use the inverse of y equals f of x to get x is the inverse of y, which will be an observation from the distribution with CDF f of x and PDF little f of x. And then depending on how many observations we want to simulate, you repeat this process until you have the desired number of observations. So I'm going to do an example with an exponential distribution, just sort of showing how this would work. I'm going to simulate 10 observations from an exponential distribution with theta equal to 5. In this case, my probability density function, f of x, is equal to 1/5 e to the minus x over 5. And my cumulative distribution function, capital F of x, is equal to 1 minus e to the minus x over 5. So just to kind of think about what that would look like, here's x, here's my cumulative distribution function, little f of x. And what I'm going to do is I'm going to randomly generate numbers between 0 and 1. I'm going to map them over here and then find the inverse function. So to do that, I need to consider y equals f of x equals 1 minus e to the minus x over 5. And I need to find the inverse. So I have 1 minus y equals e to the minus x over 5. If I take the natural log of both sides, I get the natural log of 1 minus y equals minus x over 5. So minus 5 times the natural log of 1 minus y is equal to x. So there's my inverse function. So now that I have my inverse function, all I'm going to do is I'm going to generate an observation from a uniform distribution on the interval from 0 to 1. Once I have my number y, I'm just going to calculate minus 5 times the natural log of 1 minus that value that I simulate, and it's going to give me an observation. So I used random.org to simulate random numbers between 0 and 1, and I have a list of numbers here. So for instance, this would be my first observation. So to find a value x, I'm just going to take minus 5 times the natural log of 1 minus my y value, 0.39667. And that's going to give me my first observation from this distribution. Minus 5 times the natural log of 1 minus 0.39667 gives me an observation of 2.5265, I'll round there. And now I want 10 observations, so I'm going to do the whole thing again. So here's my next number for my uniform distribution, and I'm going to find my next value x. It's going to be minus 5 times the natural log of 1 minus my new y is 0.28760. And once again, I just substitute this in. So I'm going to have negative 5 times the natural log of 1 minus 0.28760, my new simulated result, and it gives me a value of x of 1.6956 if I round to 4 decimal places. And I could continue to do this for each of the other values, and it would end up giving me a group of 10 observations that I simulated that would be coming from a distribution that's exponential with theta equal to 5. As I say, there are a number of ways you could come up with these values. I did use random.org because it's something that I know anybody could do, and I am going to go in for just a minute and show you how to do that. If you go to www.random.org, there are a whole bunch of things here. It's actually very interesting, but if you look at numbers, I want to come down and I want to go to decimal fractions. So I tell it how many numbers I want to generate. So say I want 10. I can tell it how many decimal places I want to go to. I think I chose 5 before. I can choose however many I want. I can choose how I want to display it, how many columns I want to put it in. 1. And then if I click down here, I say get fractions, and it generates the fractions, the decimals really, that are between 0 and 1. So it gives me a nice group of observations. If you wanted to, you could copy these out of here and paste them into a spreadsheet and more quickly do the calculations to find the observations that have the exponential distribution. But this is just a quick way, if you're not a programmer, that you can generate some observations that have a uniform distribution between 0 and 1. Hope this helps you get started working with simulations to generate observations from a particular distribution. This can be extremely useful. It's a tool that you may see need for later on, so I do like to cover it. It's not something that there are a whole lot of homework problems about, but I think that especially for the people who are in computer science and engineering, this can be a useful tool, so I didn't want to make sure everybody sees it. Thanks. Have a good day.